All right, today we've got a real comeback story for you. It's all about this brilliant AI idea that, honestly, was pretty much forgotten, lost to time. But now, it's been brought back to life with a super clever breakthrough that could totally change how we build the big, powerful models we use every day. So let's just dive right in. So I want you to think about this for a second. In the world of AI, everything moves so fast, right? We're always chasing the next big thing. But what if the secret to our next leap forward isn't something new at all? What if it's an idea from the past, one that got left behind? That's exactly what we need right now. So let's meet the hero of our story, or maybe the forgotten hero, the universal transformer, or just UT for short. This was this really elegant, powerful idea that offered a totally different way of building the kind of huge neural networks we rely on today. So, what was the big deal with the universal transformer? Well, it all comes down to this idea called recurrence in depth. See, instead of building a model with hundreds of totally separate, unique layers, a UT has just one layer, or maybe a tiny group of layers, that it just uses over and over again. The sharing of parameters makes it super efficient, and it turns out really good at tasks that need complex step-by-step thinking. To really get the difference, picture this. A standard transformer is like a giant factory assembly line. Every single station has a different worker with a very specific tool doing just one small job. It's effective, yeah, but you need a lot of different workers. The universal transformer, though, that's more like a single, multi-talented master craftsman. They have one amazing set of tools, and they just use them again and again, skillfully, to build something incredibly complex. It's just a way more elegant and parameter-efficient design. Okay, so if this idea was so great, why did it get forgotten? Well, every good story has a villain, or at least a major obstacle. And for the universal transformer, it ran smack into a huge wall called the parameter compute ratio problem. Here was the fundamental problem. Since you're reusing the same small set of parameters, the only way to make the model bigger and more powerful, to compete with today's massive language models, is to make that single shared layer absolutely enormous. And when you do that, the amount of computation you need just explodes. It becomes so expensive it's basically unusable. And that's the catch-22, right? To get more power, you need more parameters. But with a UT, the only way you can add those parameters, by making that shared layer wider, creates this insane computational bottleneck. So you end up with a model that might be really smart on paper, but is just impossibly slow and way too expensive to ever run in the real world. And hey, don't just take my word for it. The researchers behind the paper we're talking about today, they spell it out perfectly. They basically say that, despite all their potential, UTs just weren't compute efficient enough for the huge language modeling tasks that are common today. And so this amazing idea just kind of faded away. But here's where the story gets good. Here comes the breakthrough. The solution was to take that old idea, the universal transformer, and combine it with a really powerful modern technique, the mixture of experts, or MO. This is the key that brings our forgotten hero roaring back. So how does this mixture of experts thing actually solve the problem? Well, imagine you've got a workshop with, say, hundreds of specialist craftsmen. These are your experts. Now, when a new job comes in, instead of waking everybody up and having them all work on it, you have a really smart router who looks at the job and says, okay, for this task, I only need you and you. It calls on just the 2 or 3 specialists who are perfect for that specific job. The rest just hang out. That way, you get the combined knowledge of the whole workshop, but you only pay the cost for the few you actually need. And that is what makes this whole thing so incredibly efficient. The model has hundreds of these experts ready to go, but for any one thing it needs to do, how many does it actually call on? A tiny fraction. We're talking like 2 experts out of hundreds. This completely solves that compute problem. It's literally the best of both worlds. But, it wasn't quite as simple as just slapping MoE onto the old design. To make this combo really sing, the researchers had to invent 2 brand new things. These are kind of like MoEUT's secret weapons. The first one is called layer grouping, and the second is a really clever new way of doing normalization called the peri-layernorm scheme. Let's just quickly break down what these actually do. So first up, layer grouping. The idea here is instead of just repeating one single layer over and over, like A, they found it worked much better to have a small team of layers, maybe 2 to 4 different ones, that repeat as a single block. So it's more like AB, AB, AB. This lets the model perform more complex multi-step thinking on each pass, and their experiments showed this was the sweet spot. The second secret weapon is a really neat technical fix. See, standard transformers use a technique called peri-layernorm, but that actually causes a bunch of problems when you're sharing layers. So these researchers came up with peri-layernorm. Instead of putting the normalization right in the middle of the main data path, this new method kind of applies it around the path. And this little change solves some really critical signal issues and just makes the whole shared layer system stable and way more effective.
Okay, so we've got the theory, right? A forgotten design brought back with a powerful new technique and a couple of secret weapons. But did it actually work? This is where the story gets really, really cool. Let's look at the performance. And the results are honestly pretty shocking. When they tested it on the C4 dataset, MoUT delivered the exact same high-quality results as a normal transformer, but it did it using way less computational power. That is a massive, massive win for efficiency. And get this, it's not just about being more efficient. This chart shows that on a few really important language benchmarks, their 244 million parameter MoEUT model actually outperformed a standard transformer of the exact same size. Yeah, the improvements are small, but they're consistent. It's not just cheaper to run, it's actually a little bit better. The researchers themselves sum it up perfectly. They say MoEUT is the first ever universal transformer that manages to beat standard transformers on these big language tasks, while at the same time using way less compute and memory. This is it. This is the moment our forgotten hero makes its triumphant return. So what does all this mean? I mean, why should we care that one old AI design got a second chance? Well, let's zoom out for a second and look at the bigger picture here. This whole story, I think, teaches us a really important lesson about innovation. It's not always about some brand new, out-of-the-blue idea. Sometimes the really huge breakthroughs happen when someone has the vision to look back, find a genius idea that was maybe just ahead of its time, and use modern tools to fix the one thing that was holding it back. MoEUT is a perfect example of that. And that kind of leaves us with this one last fascinating question to chew on. As we're all racing to build bigger, better, more powerful AI, could it be that the next truly game-changing breakthrough isn't something new at all, but something old, just waiting in some forgotten research paper for the right person to come along and unlock its true potential? Thanks for tuning in.